Hi, good day, everyone. I'm Kai Wang from Henderson, Nevada, USA. Today, I will present my research results on generalization of Fibonacci numbers. So let's start from beginning. The famous Fibonacci numbers f of n is a sequence of integers. Start with 0 and 1. Then the subsequent numbers are equal to the sum of two previous numbers. The Lucas numbers is a companion sequence of Fibonacci number. It starts with 2 and 1. Then the subsequent numbers are equal to the two previous numbers. In other words, they satisfy the recurrence relation a of n equals to a minus 1 plus a of n minus 2 for n greater or equals 2. Then x squared minus x minus 1 equals 0 is the characteristic equation. Let u and v be the roots of this equation. We then have benign formulas for Fibonacci numbers and the Lucas number. For Fibonacci numbers, f of n equals u to nth power minus v to the nth power divided by u minus v. For Lucas numbers, L of n equals u to nth power plus v to nth power. Both f of n and L of n have very elegant sum formulas. F of n is equal to I plus j factorial divided by I factorial times j factorial, where I and j are the indices satisfy I time plus 2 times j equals n minus 1. Ln is equal to the sum of n times I plus j minus 1 factorial divided by I factorial times j factorial, where I and j are the indices satisfy I plus 2 times j equals n. Next, I will talk about Girard-Warning formulas and its relation to Lucas numbers. Fx is a monic polynomial of degree k with coefficients a0, a1 up to ak, with a0 equals 1. We assume that f of x has distinct roots, x1, x2, up to xk. Then the Girard-Warning formula is the following. The sum of nth powers of roots is equal to a sum of products of powers of roots multiplied by with n times factorials of sum of powers minus 1 and divided by the product of factorials of the powers. In the formula, the indices j1 up to jk, which are the powers of the roots, satisfy j1 plus 2 times j2 plus and so on, plus k times jk equals n. In Bennett's formula for Ln, is equal to u to the nth power and v plus v to the nth power, where u and v are the roots of the characteristic equation. So we may consider the sum of nth powers of the roots as a generalization of Lucas numbers. In the next formula, I'll put the information in previous slides in a table so we can compare the information side by side. In the first column, we have a Binet formula and some formula for Fibonacci numbers. In the second column, we have Binet's formula and some formulas for Lucas numbers. We also have a definition and some formula for the generalization of Lucas numbers. The question marks in the first column indicate that we shall have a generalized Fibonacci numbers, which is analogous to the generalized Lucas number. And the next question mark indicates we shall have a sum formula for generalized Fibonacci numbers, which is similar to the Girard-Wardin formula. And this is the motivation of this research, to find a nice generalization of Fibonacci numbers, which have a nice sum formula. There are many generalizations of Fibonacci numbers. They are just too numerous to be discussed in this short presentation. My generalization has many other generalizations as special cases. In the next, I will show the form of my generalization of Fibonacci numbers and the form of the new sum formulas. We will define a generalization of Fibonacci numbers as a sum of powers of roots divided by something. We will have a sum formula which is equal to the sum of the products of powers of the coefficients with a quotient multiplied with the quotients of factorials. In the next slide, I will give more details on what new sum formula will look like. Now, this is what I expect for the new formula. Okay, it's a summation of product of powers of the coefficients times quotient of factorials, which is I plus 1, J1 plus J2 plus up to JK factorial divided by J1 factorial times J2 factorial times JK factorial, where the indices satisfy J1 plus 2 times J2 plus K times JK equals N plus something. In the next, I will show a generalization of Fibonacci numbers, which involve the derivative f tick x of the polynomial fx. Okay, let f tick x to be derivative of fx. And Pn is a generalization of Fibonacci numbers, which is defined by the following formula. P of n equals to the sum of xi to the nth power divided by ft, that's a derivative of f at its value xi. And so it's very similar to the definition of Q of n. And if f of x equals x squared minus 1, x squared minus x minus 1, then P of n is a Fibonacci number. If f of x equal to x cubed minus x squared minus x minus 1, then P of n is a Fibonacci number. In the next formula, next slide, I will give a detailed sum formula for the generalized Fibonacci numbers. Fx is, as before, is a polynomial with coefficient of degree k with coefficients a0, a1 up to ak. Then the formula, the sum formula is P of n equals to summation of powers a1 to the powers of j1 times a2 times j2 and ak times up to the power of jk and times a power of -1, then times the factorial j1 plus j2 of plus jk factorial divided by j1 factorial times j2 factorial up to jk factorial. Okay, the indices j1, j2, jk satisfies j1 plus 2j2 plus up to kjk equals n minus k plus 1. Next, I want to talk about generating functions for generalized Fibonacci numbers and generalized Lucas numbers. Well, in fact, I use these generating functions to prove this sum formula. With my definition of generalization Fibonacci numbers, and the generating function is equal to x over 1 divided by f of 1 over x. And generating function of q equal to 1 over x times f tick of 1 over x divided by f of 1 over x. And the general function of q equal to general function of p times the derivative of f at 1 over x. Okay. And using the formula, we can prove the following identity. Q of n equals to f tick of p of n. Here, the p, we use a convention that f for a polynomial g of x, then g of a sequence or entry of sequence equals to the sum of the sequence. Use the coefficients of the polynomial as the coefficients. Let me make one more remark. We can also use this general function for the px to prove the sum formula for px. All definition of generalized Fibonacci numbers and generalized Lucas numbers does not include random sequence, but any random sequence can be proved is a linear sum of generalized Fibonacci numbers and generalized Lucas numbers. So we can apply all formulas to random sequence. In this sequence slide, okay, we show the definition of random sequence. Wn with initial value A and B, and the recurrence relation Wn equals P times Wn minus 1, the minus Q times Wn minus 2. And we usually use the notation W sub n square bracket A, B, and P and Q. We need new functions in the formula. Let T of n equals 0 if n is odd, and let T of n equals minus Q to the 1/2 of power of n. Then if n is even, then W of n is equal to A times T of n plus summation of P raised to I minus 1's power times minus Q to the j's power, then times B times I plus P times A times j, then times a factorial, which is I plus j minus 1 factorial divided by I factorial times j factorial. Okay, here the index I start from 1 and j start from 0, and satisfy I plus 2 times j equals n. In the next 2 slides, I'll present some examples which shows how to use my formulas to get the generating functions, and also the identities between Q of n and P of n. Like for Fibonacci numbers, we have Q of n equals 2 times P of n plus 1 equals minus P of n. This is the second slide for examples. For example, like the last one, and the polynomial is x cubed minus x squared minus 2x plus 1. Then the general function is equal to x squared divided by 1 minus x minus 2 times x squared plus x cubed. And general function for q equal to 3 minus 2 times x minus 2 times x squared divided by 1 minus x minus 2 times x squared plus x cubed. And the entry q of n equal to 3 times entry p at n plus 2 minus 2 times entry p at n plus 1, then minus 2 times p of n. Yeah, this is the end of my presentation. I'm welcome any comments and suggestions. If I have any questions, I will try to answer or online, or maybe I can write emails to answer any kind of questions. And I also have, I post most of my research results on ResearchGate, and there are many similar results regarding integer sequence. I also have posted some of my papers but way back to 1972. That's my thesis. It's all there. Okay. Okay, thank you. This is the end of my presentation. Bye.